I welcome you all for this presentation. In this presentation, we are going to discuss about prime numbers. This is the overview of this presentation, introduction to prime numbers, then Fermat's theorem, Euler-Torsion function, then Euler's theorem, primality testing, Miller-Rabin algorithm, Chinese remainder theorem, followed by summary of this presentation. Why we need prime numbers in cryptography? This is some part we discuss in the number theory also, but basically in the public key cryptography, prime numbers plays a vital role. Now we are in the third unit, that is public key cryptography. So in the public key cryptography, we all aware that it is the asymmetric key cryptography, meaning is the sender is performing encryption using one key and the receiver is performing the decryption of the encrypted message with the related some other key, okay, private key. So in the two parts, that is sender side as well as the receiver side, different operations happen, that is different keys are used. So how to generate a key? Always in the public key cryptography, we are generating very large prime numbers. So small prime numbers means we know that it is a prime number, but very large prime numbers we don't know. So we have to check whether it is a prime number or not. So in order to check that, we need to understand the characteristics of prime numbers. So only here we are discussing about prime numbers. In our syllabus, we are having the Chinese remainder theorem only after Euclidean algorithm. Euclidean algorithm already we discussed before cycle test 1. So here we are not going to discuss here. The main objective is to discuss about Chinese remainder theorem. Before that, we need to know about prime numbers. So only we are discussing first about the prime number concepts and theorems. Finally, we are discussing the Chinese remainder theorem. So prime numbers we all aware in school days, even 4th, 5th standard itself we have studied about the prime numbers. So prime numbers means only have divisors of 1 and self. So they cannot be written as product of other numbers. That is the prime number. So here 1 is a prime only, but we are not considering that 1 as a prime number. That is not interest. So only we are just telling that it is having divisors of 1 and itself. So the example for prime numbers are 2, 3, 5, 7 and 4, 6, 8, 9, 10. Why these numbers are not prime means here we are having more divisors. 4 we are having divisor 2, 6 we are having divisor 3, 8 we are having divisor 2, 4, 9 we are having divisor 3 and 10 we are having divisor 2 and 5. So we are having more divisors. So prime numbers means it is having divisors of 1 and self. So the numbers which are not having the divisors as 1 and self, those numbers we are calling it as a composite number. They are not prime numbers. So prime numbers are central to the number theory concept. So some of the list of prime numbers less than 200, these numbers we all are aware, that is 2, 3, 5, 7, 11, 13, 17, all these numbers we are aware. But if you are having very large prime number, at that time only we don't know what number is given means we can't easily tell. If it is an even number we can easily tell. But odd number we can't easily tell whether it is a prime or not. For that we are having many primality tests. Later on we can see that. Next is a prime factorization. So any number can be written, that is any composite number can be written as a product of prime numbers. That only we are calling it as a prime factorization. So to factor a number n, we have to write it as a product of other numbers, that is n equal to a into b into c. And here factoring a number is relatively hard compared to multiplying the factors together to generate the number. So the prime factorization of a number n is when it's written as a product of primes, that is here 91, it is not a prime number, but we can write this number as a product of prime, that is 7 into 30. Likewise, here you see 3600, it is a even number, so definitely we know it is not a prime number, but we can write it as a product of prime number. So how we have to get this? In earlier school days we used to write like 2. We can divide by 2, so we are getting 1800. Then 2 we are getting 900, 2 we are getting 450, again 2 we are getting 2, 2 and 5. Then we are going in for 3. Likewise it goes on up to 0, right? So we can write the factors like 2 power 4 into 3 square into 5 square. So it is also a product of prime numbers only. So the general representation representation for prime factorization is A equal to pi of P belongs to P power AP. Next is relatively prime numbers. Already we know what is the relatively prime number. In Euclidean and extended Euclidean algorithm itself, we discussed what is the relatively prime number. That is, if you take any two numbers, the GCD of two numbers is 1, then those numbers we are calling it as a relatively prime number. So meaning that two numbers A and B are relatively prime if they have no common divisors apart from 1. Example is 8 and 15 are relatively prime. Since factors of 8 are 1, 2, 4, 8 and 15 and 1, 3, 5, 15 and 1 is the only common factor. So only we are calling here 1 is the common among these two factors. Others are different. So 1 is the only common factor. So GCD of this 8 and 15 is 1. So only these numbers we are calling it as a relatively prime number. Conversely, we can determine the GCD by comparing their prime factorization using the least powers. This way also we can find it. Next is Fermat theorem. In Fermat theorem, we have to remember two formula. One is A power P minus 1 congruent to 1 mod P. Here P is a prime number and there is a relation between A and P, that is those two are relatively prime. That is P is a prime and GCD of A comma P equal to 1. So here prime numbers plays a vital role in Fermat theorem, or the other name for Fermat theorem is Fermat's little theorem. So here relatively prime. So only we have discussed what is a prime number, what is a relatively prime number. In these algorithms they are used. So only we discuss those things. So another way to write this Fermat's little theorem is A power P congruent to A mod P. Mainly where this Fermat's theorem or Fermat's little theorem is used means it is mainly used in public key and primality testing. So here you see 3 power 12 mod 11. So how we can write 3 power 12? 3 power 11 into 3 mod 11 we can write. So what is 3 power 11? A power P congruent to A mod P. So 3 power 11 mod 11 is 3. So 3 into 3 mod 11, that is 9 mod 11. So this way we can find the value of any modulus operation also using the Fermat's theorem. Next is Euler-Torsion function. Actually, we want to discuss Euler's theorem, and in the Euler's theorem, we are having a function called Euler-Torsion function. So first we are discussing about Euler-Torsion function, then only we are discussing about the Euler's theorem. So here in the Euler-Torsion function, it is represented as pi of n. Euler-Torsion function, it is represented as pi of n. So when doing arithmetic modulo n, we are having complete set of residues. That is complete set of residues in the sense 0 to n minus 1. Suppose n value equal to 7. So the residues are 0 up to 6. These are the residues. But in the residues, we can get some reduced set of residues. So reduced set of residues is those numbers which are relatively prime to n. So when we are calling it as reduced set of residues means it is relatively prime to n. Say for example, n equal to 10, the complete set of residues is 0 to n minus 1. So 0 to 9, and reduced set of residues is each and every number we have to check with the n, and if that number is relatively prime means then we are writing it in the reduced set of residues. So 0 it is not, 1 comma 10, 1 and GCD of 1 and 10 is 1 only, so 1. 2 and 10 it is not 2. We are having a common factor as 2, so it is not relatively prime. 3 and 10 GCD is 1 only, so it is coming in the reduced set of residues. Likewise we have to find. So for n equal to 10, the reduced set of residues are 1, 3, 7, 9. So what is the Euler-Torsion function? So the number of elements in the reduced set of residues is called the Euler-Torsion function. Next is the Euler's theorem. It is a generalization of Fermat's theorem, that is A power pi of n congruent to 1 mod n. Here for any a comma n where GCD of a comma n equal to 1. Now you please recall in the Fermat's theorem what formula we have discussed. A power p minus 1 congruent to 1 mod p. So here pi of n is, what is the value? Pi of p is p minus 1. So pi of n is n minus 1. And in order to define this pi, always we can write it as a factors of prime. So pi of n value, if you know, means we can easily write, we can easily find out the value of the Euler-Torsion function. So only here pi of n congruent to 1 mod n. Here GCD of a comma n equal to 1. These are some of the examples. So another way to write is there a power p congruent to a mod p. Here why it is written as a power pi of n plus 1 means what is pi of n? It is n minus 1. So pi of n plus 1 is n minus 1 plus 1. So here this cancel out and it becomes n. So it is similar to a power p congruent to a mod p. So a power pi of n plus 1 congruent to a mod p. So this way we can find. Here if some modulus example is given means we have to use this formula and we have to find out the value easily by applying to this formula. This is about the Fermat theorem and Euler's theorem. Then primality testing. Mainly we need to use very large prime numbers. So traditionally see using trial division, that is we divide by all numbers primes in turn less than the square root of the number, but it works for small numbers. So it is not very easy to find out a prime number. Randomly if we generate something and we need to check means it is difficult. So we are using some primality test, statistical primality test based on the properties of primes, for which all prime numbers satisfy the property but some composite numbers called pseudo primes. So what is pseudo prime means? The primality tests tell that it is inconclusive, that is it can't conclude that whether it is prime or not. So that may be prime or may not be prime. So two cases we can consider. So the prime numbers means it is prime only, but may not be prime, right? Some numbers are there, no? So those composite numbers we are calling it as a pseudo prime. So can use a slower deterministic primality test. So very famous and important primality testing is Miller-Rabin algorithm. So it is a test based on prime properties that result from Fermat's theorem. So in order to discuss this algorithm only, we already discussed about the Fermat's theorem, because the main thing used here is Fermat's theorem only. So the algorithm is test of n is find integers k, q, k, where k greater than 0, q odd, so that n minus 1 equal to 2 power k into q. So we are selecting a random integer a, that is 1 less than a less than n minus 1. And if a power q mod n equal to 1, then we are returning it as inconclusive. For j equal to 0 to k minus 1 do. And if a power 2jq mod n equal to n minus 1, then also we are returning inconclusive. Here inconclusive in the sense it may be prime or not prime. So may or may not be a prime. So this not prime case only we are calling it as a pseudo prime. Okay, otherwise we are returning a composite. So the primality Miller-Rabin algorithm, it is not definitely telling or it is not concluding that it is a prime. So it is giving a result like it is a composite number or inconclusive. That inconclusive may be a prime number or may not be a prime number. That is the case. Next, the probabilistic consideration, that is if Miller-Rabin returns composite, the number is definitely not prime. Otherwise, it is a prime or pseudo prime number. So chance it detects a pseudo prime is less than 1 by 4. So hence if repeat test with a different random, then chance n is prime after t test. That is probability of n prime tests after t test is 1 minus 4 power minus t. So here if t equal to 10, then probability is greater than 0.999. Then use the deterministic AKS test. So after Miller-Rabin, for the conclusive part, we have to use the AKS test to find out whether it is a prime or not. Next is a prime distribution, that is prime number theorem states that primes occur regularly every log n integers but can immediately ignore the evens. So mainly in practice we need only test 0.5 log n of n numbers of size n to locate a prime. So here this is only the average value. Sometimes primes are close together also, other times they are quite far apart. Next is a very important algorithm, that is the theorem, that is the Chinese remainder theorem. It is also called as CRT. So it is mainly used to speed up modulo computations, and if working modulo a product number, it is given like this: x congruent to a1 mod m1 x congruent to a2 mod m2 up to x congruent to ak mod mk. What is the first step is we have to work on the capital mod. Capital mod is nothing but it is a product of all small moduli. So m1, m2 up to mk. So the Chinese remainder theorem work in each moduli mi separately, and mainly it is used to solve ongoing equations with one variable but different moduli. One variable with which are relatively prime. So what you need to check is this moduli. First you have to check whether they are relatively prime or not. Relatively prime or not in the sense the GCD of these moduli is 1. If it is that case, then only we can go in for this algorithm. Otherwise it is not possible. So since computational cost is proportional to size, this is faster than working in the full modulus m. So how we are solving this Chinese remainder theorem is we have to find m. M is m1, a product of all the moduli. This is called as a common modulus. After finding out the common modulus, individual modulus we have to find, that is m1 equal to this common modulus divided by individual moduli. M2 equal to m divided by m2, then mk equal to m divided by mk. Then we have to find out the multiplicative inverse of all this individual modulus. That is m1 inverse, m2 inverse, mk inverse. With respect to the small moduli we have to compute. Then the solution of the simultaneous equation is x equal to summation ai mi inverse mod m. So first step we are computing m, that is common modulus. Then individual modulus we are computing, that is m1, m2 up to mk we are considering. Then the corresponding inverse also we are computing. Then we are finding the simultaneous equation. Here only we are using this a1, x congruent to a1 mod m1. That a1, a2 all are used in the simultaneous equation only. Finally we are getting the answer x. So if you want to check whether the computer simultaneous equation is correct or not, directly x congruent to a1 mod m1, if you give the value means you are getting the answer for all the equations, so that whatever the value computed is correct. So I have given you 3 problems to practice. So here x congruent to this is a1 mod m1, this is m1. So first step we need to find out m equal to this m1, this is m2, then this is m3. So m equal to 5 into 7 into 8 you have to find out. After finding this m, we have to find out m1, m2 and m3. So what is m1, m2 and m3? M, whatever the value we are getting here, m divided by this m1 value 5. Then m divided by 7, m divided by 8. Then we need to find out the m1 inverse, then m2 inverse and m3 inverse with respect to m1, m2 and m3. Then we have to find out summation ai, mi inverse mod m we have to find out. This is the simultaneous equation. So once we get the value of x, we have to apply this value here and we can get this value. X congruent to whatever value we are getting, congruent to this means we are getting the answer 3. Then if you apply it to the second one, we are getting 1, third one we are getting 0. So if you get the answer, then only it's correct, otherwise it is not correct. And another thing you look into here, 8, 7, 5. These 3 numbers are relatively prime. That is the GCD of 5, 7 and 8 equal to 1. This is also an important point you have to note in this Chinese remainder theorem. Try to solve all these problems. So in this presentation we discussed about the introduction to prime numbers, then Fermat's theorem, Euler quotient function, then Euler's theorem, then primality testing, Miller-Rabin algorithm and Chinese remainder algorithm. I request all of you to practice the problems given under Chinese remainder theorem. Thank you.